And we are recording. Well, welcome to the evening of Python coding. Each time we have a demo of a different topic. Today we're having the state of the art of the state of the art. And we have quantum computing and machine learning kind of combined. I may be exaggerating a bit, but Alvaro Ballon, he's gonna explain to us in much more detail what I just said in a much better way than I can explain it. The library that we're going to be demoing today is called pennylane. And Alvaro, please take it from me because I don't know that much.
Okay, sure. Welcome everyone. Thank you for being here. Yeah, today we're going to be learning about pennylane, which is a library in Python whose intention is to be able to program quantum computers. It was definitely born as a way to do what is called quantum machine learning, which is basically trying to do some machine learning with quantum computing, with quantum computers. But right now, it's branching off a little bit more, and it's a little bit more general than that. And before we can do nice stuff with quantum computers, such as quantum machine learning, we need to learn a little bit the basics. So I want you guys to tell me in the chat, like, I don't know, from 0 to 10, how much do you know about quantum computing? Just throw a number there. Okay, we got some zeros, some sevens, some ones, some zeros, a -1. Okay. Yeah. It's all good. I will assume that no one has heard much about it or know much about it. So basically, it's funny that we were talking about cherry-picked examples that run much faster in this new framework. But this is kind of what is happening with quantum computers now. Quantum computers are devices that instead of using bits, they use something called qubits. So the way in which the hardware works is very, very different from how our current, what we call classical hardware, works. Because these qubits physically behave really differently from what we're used to.
Yeah, it was up. Like, how did
Someone join us with has to unmute himself.
Yes.
I'm trying to figure out who is making noise. Okay.
Thank you.
Okay, go ahead.
Okay. Yeah, sorry about that. So the framework of how the hardware works is very differently. It works very differently from the computers that we have now. And what we know that they can do is, like, there's very, again, cherry-picked examples in which these quantum computers in the future, when they're completely developed, will be able to do things much faster. Some examples that we know are search problems, searching in a list. Instead of looking through most of the list, you can do in like it scales with the square root of the length of the list if you want to look for an item. So that's nice. Prime factoring, maybe that's something also that you have heard that quantum computers should be able to do much faster. But what we're looking for in Xanadu in particular are for more applications of these quantum computers. So if we had a quantum computer right now, we probably wouldn't really know what to do with it. If some aliens came and gave us a quantum computer, hey, you have this, we still wouldn't know what to do with it. So we are looking to for new applications of quantum computing that will be useful for industry. That is something that we can sell to people, that people value and they are willing to spend their money on something, that a calculation that they want to perform. So far, that doesn't exist. Okay, so I want to be very clear that this is not the point where we are at, but we hope to get there, and we'll see. Always from this fundamental research and new discoveries come around. So that's very, very exciting. So what pennylane is, it's basically a Python library that will help us program quantum computers. So let's go into a little bit of what is quantum computing. So I told you a little bit about bits and qubits. Bits are the normal bits that we use in computers. Qubits are a little bit different. You'll see here in the screen that I wrote this psi enclosed by this bar and this and this bracket here. So that's how you represent a qubit. We are going to represent this qubit's name. The name of the qubit is psi, just because it's something that people like to use. And then we're going to, you see this 0 here and this 1 here. This 0 is like the value of the bit is 0. And this 1 is like the value of the bit is 1 that we usually have in normal computers. The difference in quantum computers is that the laws of nature at a very small scale of atoms, subatomic particles, and lights allow us not only to have zeros and ones, but allow us to have this weird entity, which is a sum of 0 and a 1. It's like, if you've seen linear algebra, this is called a linear combination of zeros and ones. So this alpha here turns out to be a complex number, and this beta here is also a complex number. So a bit now can not only be just 0 and 1. Was there a question?
No, someone joined and didn't mute themselves. So
okay. Sorry about the math. Be prepared for some linear algebra. Yes, so basically how we represent this is a vector, okay? So this is a vector, a column vector, which has this alpha, which is a complex number, and this beta, which is also a complex number, okay? So our bits are no longer just zeros or ones, they are actually vectors, and vectors whose entries are complex numbers. That is the big difference, and this allows for so much more. This is not the only difference, as we will see later, but yeah, this new object that we calculate is called a qubit, and is basically a linear combination of bits. And we also call this a superposition. Now, you may have seen something in the media, I don't know, amongst millennials and Gen Z, this has become really popular, that people talk about Schrodinger's cat, saying, oh, like if 0 represents the cat being dead and 1 represents the cat being alive, then what does alpha 0 plus beta 1 represent, right? What does this vector represent for the cat? Is this in state like between alive and dead? Is it alive and dead at the same time? Some people just like to philosophize about this, and the answer to these questions is, what does this actually represent? Is we don't know. It's just that matter at small scales behaves in ways that are not very intuitive to our brain, and it's also not very precise to say that it's 0 and 1 at the same time. Okay, it is just a new object, and this new object is a vector, and this is the way in which we model nature at those scales. So that's it. Take it at face value. I don't know why it works. It works. No one understands why it works, but it works. So let's talk about a little bit of a classical setting. Classical is not quantum. When we have gates that act on bits. So for example, if you are acting on one bit, I guess the only interesting gate that you can act on one bit is the NOT gate. The NOT gate basically just turns a bit 0 into a bit 1, and a bit 1 into a bit 0. We only have zeros and 1. The other only gate possible would be that takes 0 to 0, 1 to 1, but that does nothing, so that is not considered for us a gate. So this is what we can do classically if we only have one bit. Okay, the only thing that we can do. But what if we have one qubit? Then our possibilities multiply. Whew. So qubits are vectors. Okay. So qubits are vectors, and there are ways in which you can transform a vector into another vector. And the way in which you do this, if you are having some linear algebra flashbacks, is by multiplying the vector by a matrix. Okay, so this matrix multiplies the vector on the left and turns it into something else. So, for example, this 0, this gate here, which we call the Hadamard gate, will turn 0 qubit into this combination of qubits. Is there a question?
You can go on. It's all okay. It's people joining in. The mic is on. This is what you're hearing.
Okay, that's good. I'm just making sure.
You're good.
Okay. So yeah, and this 1 is transformed by this gate to this other vector, to the vector 1 over square root of 2 minus 1 over square root of 2. So there's ways in which we can non-trivially transform vectors into something else. So you see that we have many more possibilities when we have qubits to transform them into something else. And this is completely different to 0. We are able to operate with vectors with only one gate. This X, for example, is what would be the equivalent. This is called a poly-X gate. And this is what would be equivalent to our previous NOT gate. The NOT gate basically just reversed 0 to 1 and 1 to 0. So this does the same. This takes a 0, it takes it to 1, and the 1, it takes it to 0. So these also exist in quantum computing. But you could have basically anything, any matrix that has determinant 1 here. You can apply it to these qubits, and it will give you a different result, which you can manipulate more. And what is the advantage of this? Why is this actually useful? Because if you can take this 0 into something that is this combination of 0 and 1, then you could keep applying other different gates that act on 0 and 1 simultaneously. Okay, so you could have, so instead of me calculating first what happens for 0 and then what happens for 1, I could just act on these combinations of 0 and 1 and figure out what happens at the same time, what happens for 0 and what happens for 1 at the same time. And that allows for some parallelization of quantum computing. This is a little bit imprecise because it requires a little bit more than this, but this is kind of where it comes from. Yes. Are there any questions? Have I lost people by now by going into linear algebra?
You're going in good pace. Please go on.
Okay.
You're teaching. If I'm not asking, then this means you're good, and you're good.
Okay. So
you know what? I'll ask a question just because at the beginning you showed us this like the Schrödinger cat idea. It's like there's also the idea of like, for those who don't know, the cat is alive and dead at the same time, and until we check, we don't know whether it happened because the cat is inside the safe that we don't know what's inside. But the numbers you showed before, the 0 and the 1, let's say 0 is dead and 1's alive. That if I have a number like 0.6, does it mean that there's 60% chance that the cat is alive?
Yes, we are going to see that in a moment.
Okay. So you see, I'm asking. Go on.
Okay. Yeah, let's keep going. So yes, we're going to see that in a moment. But I want to talk about a little bit about what happens when you have 2 bits. With 2 bits, that's where the power of our current computers comes, right? You can do binary operations such as AND or etc. You can apply all these types of gates. And the same happens in the quantum world. In the quantum world, we can do operations on 2 qubits. Mm-hmm. On 2 qubits. But the thing is that 2 qubits, yes.
You're hearing an echo. You're fine. I'll close that for you. Go ahead.
Okay. Yeah, on 2 qubits. So for example, this one here that you see, again, this symbol enclosing a 0, 0 means that the first qubit is in 0 and the second qubit is 0. This one means that the first qubit is 0 and the second qubit is 1, and so on. So these represent these states that we understand. But again, we can have this superposition. We can have a combination of the qubits being both in 0 plus the qubit being in 0, 1, or 1, 0, or 1, 1. So we can have this combination of different states of the two qubits. And again, we represent this as a vector. So this alpha corresponds to 0, 0, this beta to 0, 1, this gamma to 1, 0, and this delta to 1, 1. So we are going to be seeing these vectors when we program the pennylane. Pennylane is basically going to spit out these vectors. Okay. So as an example, for a 2-qubit gate is the control NOT gate. Of course, also exists in classical computing, which basically, if there's a 0 on this qubit up here, so you will see this kind of notation now, where we're going to represent the qubits as kind of these wires. Okay, so this wire up here is one of the qubits. This wire down here is the other qubit. And this circle and circle with a cross here plus this line, that just represents the gate that is acting on the two qubits. And what we see here is that if the first qubit is 0, that the first qubit doesn't change. This gate does not change the first qubit here, but it changes the second one, but it does so conditionally, right? The qubit will remain the same. The qubit down here will remain the same if the one up here is 0, but they will switch if the one up here is 1. Okay, so that's what the C0 operation is. And this can be represented again as a matrix. Okay, so this operation again is a matrix with determinant 1. Okay, so then let's go to the question that Jacob was asking. So what does those, what do those alpha and beta represent in a qubit? So here we have our qubit again. So what that actually means, so we don't really see in our daily lives, we don't see a bit in a computer being in this strange superposition of 0 and 1, right? We just see them either in 0 or we either see them in 1. In the same way that, for example, if this represented a dead cat and this one cat that is alive, we don't see a cat that is in a superposition of dead or alive. And that is because in quantum computing and in life in general, what we see is a measured version of the qubit. So to extract information for the calculation, we kind of have to, we can calculate with the qubits in this way by multiplying them with matrices and getting a result at the end. But at the end, we have to measure, okay? At the end, we have to what is called perform a measurement. That is, we need to extract information from the qubit. And the qubit can only be actually in 0 or 1. It cannot be in anything else when we measure. Okay, when we measure, the qubit will basically say, oh, I'm a 0 or I'm a 1. It will not, we will not be able to see it in this superposition. And what these alpha and beta represent is the probability of measuring it in 0. For example, alpha, when you take the complex module and square it, alpha squared represents the probability of measuring 0. So once if I have this at my end of the calculation and alpha squared is 0.6, then I will have a 60% probability of measuring 0. And then I would have a 0.4 probability of measuring 1. So this is where it all kind of went down the drain, right? It's just, okay, yeah, I can do these operations with matrices, but in the end, when I measure, I can only measure one thing. And moreover, you're telling me that this outcome is only probabilistic, that I will only be able to see I will only be able to measure 0 or 1 probabilistically. So how do I know that the algorithm is working 100% of the time if it has this probabilistic nature, right? So this is where what kind of slows down quantum computing in many aspects. But if we are smart about it, we can do many things. We can actually extract information from these statistics. We can encode the calculations in these coefficients and have all the information that we want just from those coefficients. Or we can repeat the calculation many times. We can repeat the algorithm many times and see just what alpha and beta were, because we can extrapolate. And maybe it's not too costly to repeat the calculation many times and just get the statistics. The other thing is that much smarter people, what they do is they have ways in which the quantum algorithm actually only works in one shot, and it will give you like 100% probability of, it will be something like beta is 0 here, and it gives you some result with 100% probability. So that is more difficult to do, but it is possible to do. So in the end, this probabilistic nature does not really affect much. Okay.
Alvaro, someone is asking a question. I'm going to read it. Is the role of the algorithm to implement the digital logic of a gate?
Yes. So basically, an algorithm is basically a sequence of gates, right? That will act on the qubits. They will act as a sequence of gates. And if you choose these gates in a smart way, you can do interesting calculations with it, like the ones that I was mentioning at the beginning. So I've shown you only some of these gates, but we have so many more, and there's so many available that we can do a lot of things. And some of those algorithms can be really, really, really interesting. So yeah, let's move on to pennylane. Pennylane is basically what is going to let us apply gates to the qubits and build this sequence of gates that I was talking about and calculate it. It allows for much more, actually, because pennylane also allows you to actually run your algorithms on actual quantum computers. And it also is kind of built for a particular application of quantum computing that is called quantum machine learning. I don't know if we'll get to that here, but it is in the presentation and you can look at it later. Okay, so let's start building our first quantum circuit in pennylane. So if you have already installed pennylane, just pip install pennylane and you'll have it. And the first thing that we have to do, as with every library, is to import pennylane. So these are the two commands that we'll have to write in our Jupyter notebook, which are already written for you. But yeah, we usually import pennylane as QML for quantum machine learning. And from pennylane, there's an installation of NumPy that is within pennylane. And that's actually very useful for some things that we want to do within pennylane. So it's recommended that you, when using pennylane, install this particular installation of NumPy. Okay, so yeah, just import them by writing that, or well, if you're following the notebook, that's already written for you. And then what we next have to do is choosing our quantum device. So this is a little bit more advanced. Okay, the only ones that I would like you to look at are default qubit and lightning qubit. Okay, so what default qubit is just it basically means so there's other kinds of entities in quantum mechanics that are not qubits, and that's why you have to specify. But because we are doing everything with qubits, this is the one that we're going to import. The difference between lightning qubit and default qubit is just that one uses C++ with a backend code, so it can be much faster for certain things. But let's not complicate ourselves, because we're not going to do something that requires a lot of power. So let's just choose as our device default qubit, which just means, hey, pennylane, we are going to work with qubits and we don't care if you're slow. That's all this means. So the way to tell this to pennylane that we're going to work with qubits and we're going to be kind of slow is with this command, qml.device and default qubit. And then after default qubit, we're going to tell it how many qubits we are going to work with. Okay. So we also have to specify this. Usually working with 20 or more qubits is really, really slow. We are going to work with 2 because that's our first example. So yeah, we're just telling pennylane, hey, we're going to use qubits and we're going to use 2 of them. In any of the algorithms that we're going to write, qubits and 2 of them. That's it. This is all what it does. Then we are going to build a quantum circuit. So what is the quantum circuit that we are going to implement? Okay, so I already showed you these guys before. So remember, the first qubit is this one up here. This wire up here is the first qubit, and we can apply what is called a Hadamard gate. A Hadamard gate is the gate that turns 0 into 1 over square root of 2, 0 plus 1 over square root of 2, 1. Here, by the way, the qubits are always initialized in 0. Okay, so the initial vector to which we are always applying stuff is 1, 0. And it's just the vector, the qubit 0, right? And the qubit 0 is represented as a vector as the vector 1, 0. And the qubit 1 is represented as 0, 1. They're always initialized in 0, and then we're going to apply this gate to it. Then this gate to it, which is the C0, which I also introduced before. And then this other gate, which is called the poly-X gate, that I also introduced before. So let's play around with it. I'm gonna just going to share my Jupyter notebook actually here, which is also the presentation. So yeah, so here we just wanted to import pennylane as QML, and from pennylane import NumPy as NP. That's it. And then the second step, which was to the QML.device, default qubit, and YRC1.2, saying that I just want to use 2 qubits. Let me do something simpler first, because I think this presentation was actually for people that were already familiar with quantum computing. I adapted it, but I think I should do something a little bit easier. Let's work with 1 qubit first, okay? And I'm going to call this def1, and we're just telling pennylane we're working with 1 qubit. And then what we are going to do is we're going to create our algorithm. An algorithm is a sequence of gates, okay? So for an algorithm, for us, will just be a function. I'm gonna define a function, and we call these quantum algorithms, we call them quantum circuits as well. So it's very common to just define it as a circuit. Just say define circuit, and we are defining a function that we're calling circuit, okay? No arguments. Some of them will take arguments though, but for now, there's no arguments, okay? And then let's say that this doesn't do anything, okay? So yeah, let's say that it doesn't do anything. And by the way, this circuit always has to be associated to the device, okay? So pennylane has to understand that this circuit is only going to use 1 qubit. And the way that we specify this is by putting this decorator on top of our function, uml.qnode def1. Okay, so we're just telling, hey, this function is going to use 1 qubit, which was specified here. Okay, and then we're just defining a function. We're just defining a function named circuit. And let's just write this. We're going to return QML state. The state is basically just the qubit. Okay, So if I write this and then run circuits, and I will get this. I will get basically a vector, which is 1. Okay, there's this imaginary number here. I told you that these were complex numbers, but this part is 0. So this is the vector 1, 0, right? So I didn't do anything. And what was returned was 1, 0. Why is this? This is because, let me go back to my presentation. I just want to go back to a little bit of the beginning, right? So what does 1, 0 represent here, right? Remember, we represent these qubits as vectors. 1, 0 represents that this alpha is 1 and that this beta is 0. So what it just means is that the qubit that we have chosen, that we have at the end of doing nothing, is just this one, 0. There's this alpha is 1 and this beta is 0. So all what we have is the 0 qubit. Okay, so everything always starts in the 0 qubit. If we do nothing to it, we can see that that's the case. Okay, but now let's try to do something with it. And the way in which we do it is by applying a gate. Okay, so I told you before about this particular gate. Let's go there. The NOT gate, right? The NOT gate takes the qubit 0 into qubit 1 and takes qubit 1 into qubit 0. So let's apply that gate. This gate in quantum computing is called poly-X. So what we would do is QML, and there is a poly-X built into pennylane. Okay. But now we have to specify, because we usually would have more than one qubit, we have to specify in which qubit this poly-X is going to act. Okay. We only have one qubit, so it doesn't matter. But here we're going to specify that it acts on the first wire, which is the only wire. And that we do but by putting wires is equal to 0. Okay, because remember, in Python, we count from 0. So if this qubit started from the bit 0, which is represented as 1, 0, but this is going to flip it, right? Now circuit is going to flip it. So if I run circuit, it's going to give me 0, 1. Okay. Well, I'm not sharing. Sorry, I thought I was sharing this tab. So this is what I am doing. I'm going to do it again. So what we did to circuit was basically to just add this gate called poly-X and specify that it acts on the first wire. In Python, we count from 0. And basically, all that I've done is added this poly-X or NOT gate to the circuit. And once I run it, it gives me 0, 1. And what was 0, 1? Remember, 0, 1 is from here.
The opposite?
Sorry?
It's the opposite?
Yeah, it is the opposite, right? It's 1 here and 0 here. So it's turned the bit 0 in the qubit 0 into the qubit 1. So that was the NOT gate. Okay? So that one's kind of boring. Let's do something more interesting. The Hadamard gate. I introduced the Hadamard gate also somewhere over here. So what the Hadamard gate does is it turns 0 into 1 over square root of 2, 0 plus 1 over square root of 2, 1. And why is this number here so weird? By the way, why is it 1 over square root of 2? Because remember that the square of these represent probabilities. So the square of this would be 1/2, and the square of this would be 1/2. So basically, what this is telling me is that if I were to measure this state at the end, it would give me 0 with probability 1/2 and 1 with probability 1/2. So that's what this state means here. And this one kind of means the same, but the thing is that if you manipulate it later with other gates, it will give you a different thing. So let's do the Hadamard gate instead, which is more interesting. So this is all basically matrix multiplication, you know. So let's I have to keep changing tabs. Sorry. So instead of poly X, let's write Hadamard. Okay. And when we write Hadamard and return QML state, let's see what happens. So now we haven't returned a 0, 1 or a 1, 0. We have returned this number here and this number here, which are just the prefactors of the 0 and the 1, right? So this is giving me exactly 1 over square root of 2, 0, plus 1 over square root of 2, 1. Okay, so that's just a circuit with a Hadamard gate. And then you could do something more interesting, which is combine two gates. So I could first do a poly X gate, which will turn the 0 into a 1, and then do the Hadamard gate, which would act on this one. So it goes in this order, right? So first I apply the poly, then I apply the Hadamard, and then I return the state at the end. And if I run this, I get 1 over square root of 2 minus 1 over square root of 2, which is precisely what I promised here, right? 0 became 1 because of the X, and then this 1 became 1 over square root of 2 minus 1 over square root of 2, which is what we are seeing there. So most of you will say, okay, this is kind of boring. This is just matrix multiplication, and you have something fancy to do matrix multiplication. But the thing is that it's very useful to keep in mind what gates exist for quantum circuits, and this has them all built in. And of course, we can do more interesting things later. So yeah, let's go to the one that I promised now, which is something like this. So now we're working with 2 qubits, right? Now we're working with 2, and we want this specific circuit, which is a Hadamard on the first wire, a control NOT that acts on 2 wires, and an X on the second wire. Okay. So what would that do? How would I write it? Remember, the first thing that we have to do is to tell pennylane, hey, this time we have 2 qubits. So we have to tell pennylane that that's what we're going to do. So we can define another device. Sorry, I'm going to put this a little bit more up. So remember, this whole thing is just something that you'll eventually learn by heart. And then wires equal 2 because we're working with 2 qubits. And then we have to tell them, hey, this function quantum circuit, calling quantum circuit now, is going to use this device which has 2 qubits. Okay, so we do qml.qnode decorator, and specify that it's going to use 2 qubits, which are defined here. And then we define the function. Let's define the function. Let me erase it and write it in real time. So the function was, first, we need a Hadamard. So we read this from left to right, right? So first we need a Hadamard on the first wire. Okay, so let's do Hadamard wires equal 0. And we need a control NOT gate that acts that the control is on the first wire and the qubit acted on is on the second wire. So the way you do this is qml.not wires equals 0, 1. And then we need poly X on the second wire. So can anyone tell me what that would be? We are following.
We're trying.
Which one? Like it's a poly X gate on the wire number 1, right? So if I want this circuit, I have first done a Hadamard on the 0th wire, a C0 on these 2 wires, and then I need a poly X on wire
So
1.
So it will be wires equals 1?
Exactly.
Whatever
Will be poly X, which wires equal 1. Yes.
Yeah. But where did the names come from? Like Hadamard, Polyex?
From scientists, I have no idea why these are called like this. It's just some lingo that that people like to use, and you eventually get used to it. But yeah, it can be a little bit overwhelming. You just start learning some names of some very common gates that are used in quantum algorithms, and yeah, I mean, poly X should be called not. Really, it's the not gate, right? But people just like these fancy names. It is what it is.
But it's not only a not gate. There's something in like X happens after we do the C naught.
Yeah, X happens after we do the C naught.
Okay.
So let's see what happens if I return. I didn't write return. QML state here. And then we could have something, if I run quantum circuit, I run quantum circuit, it will give me this vector, but this vector is a vector with 1, 2, 3, 4 components. And why is it a vector with 4 components? It is a vector with 4 components because, as we saw before, when you have 2 qubits, the way to represent 2 qubits is as a vector with 4 components. Okay, so 1, 2, 3, and 4, where the first component represents both qubits being in 0, the second one being in 0 and one being in 1, and so on. Okay, so here, what did we get? So just learn, try to take a mental snapshot of this. But the way in which it works is you kind of counting in binary here, right? So it goes from 0, 0, the second one is 0, 1, the third one is 1, 0, and the fourth one is 1, 1. So this is how you kind of remember this order of what the coefficients of the vector represent. Okay, so here what we have, this is a number that we've seen before. This number that we've seen before, this is 1 over square root of 2. This is also a number that we've seen before, this is 1 over square root of 2. So what this is telling me is that at the end of the circuit, I have 1 over square root of 2. This is the second component, so it's 0, 1, plus 1 over square root of 2, 1, 0. So what this is telling me is that if I measure, we will have the probability of 1/2 of measuring one qubit in 0 and the other one in 1, and the probability of 1/2 of it being the reverse, that the other qubit is in 0 and the other qubit is in 1. Okay, so that's basically the basics of how this works. There's other things that you can actually return here. So for example, I could return not necessarily state, but a more realistic thing to return is the probability, because in the end, when you measure, you only measure the probabilities of measuring of a particular outcome, which can be 0 or 1. So I can write here QML probs, and I want the probabilities on all the wires. You can restrict yourself to the probabilities of only one wire. So for example, if I write this instead of a state at the end, you will get, oh yeah, it's what I already knew, that it was 1/2 that I get 0 and 1, and 1/2 and another half that I get 1 and 0. You can also ask it for the probabilities on only one wire, by the way. If you look at this, you see, okay, so if probability 0, let's just focus on the first qubit. There's a probability 0 that is 0, 1. So there's the probability, 0.5 that is 0, 1, and probability 0.5, that is 1, 0. So it will also be kind of like there's a probability of 0.5 that the first qubit is in 0, and 0.5 that the first qubit is in 1, because this is 0, 1, and this is 1, 0. This is the first term that counts. So if I want probabilities for the first qubit, I would have to do the same, then write it, and then I would get, oh, for the first qubit, it will say I have a 0.5 probability that it's in 0, and a 0.5 probability that I will measure it in 1. And there's many more things that you can return here. For example, because this is the statistics, right? This will be a statistics. You can, for example, oh, every time I get a 0, I wanted to weigh it by a -2. But every time I get a 1, I want to weigh it by a 1. So then you would get like an expectation value, like -2 times the probability of getting 0 plus 1 times the probability of getting 1. So that's also things that you can do here, but that is a little bit more involved. But you can play with the statistics in the return statements here. So yeah, okay, this is pretty much what we've done so far. Now, what I wanted to mention, just to finalize now, because I don't think we don't have much time to get really far, is that there are some gates that are actually parametric. So the other ones were these gates that these do exactly this. But there are some gates that depend on a parameter, and they will do different things depending on the parameter that you put in them. For example, this is called what is called a rotation. So it's basically kind of the intuition is that it's rotating the 0 into the 1, and that and depending on the angle that you put here, how much you rotate the 0 into the 1 will be different. So the output will be kind of different depending on the parameters. So let's just experiment with that. So let's just do with one wire, just to show you how this works. So we could have this rotation gate, which is called Rx. And let's call this params an angle. And this Rx, not only it needs wires like the one before, but it also needs the parameter, the angle. And it's going to act on wire 0, and then I'll return QML state. And here you go. If I run this with an angle, I don't know, 0.5 or something, then I will get something that is not 1 over square root of 2, 1 over square root of 2. It's something different, right? So this allows me to play more because I have a parameter to play with in the gates. So it will be able to return different things. So as an exercise, once we're done with this, you could try, for example, creating a circuit with 5 parameters and 3 wires that create something like this. Okay. And you can start playing more. Like I think by now you have the basic knowledge of like how these quantum algorithms work and how you would program them in pennylane. You're just basically reading from right to left, writing all the gates, and computing an outcome that is a vector. So that is basically the very, very basics of pennylane. If you want to learn more, there is definitely more in this presentation that I wasn't able to cover. But if you want to learn more and are really, really interested and want to master pennylane, I'll recommend it's called our codebook, which are our main learning material for pennylane and quantum. So you can learn all about quantum here. It will assume that you know Python, and it will assume that you know linear algebra, which is kind of what I have assumed for this talk as well. But this is a good resource that you could use to start learning and getting familiar with pennylane, and I think it's very friendly. So I really do motivate you to use it. Also, if you are interested in learning more about quantum and start like testing your quantum programming skills yourself, I would highly recommend that you sign up into our events such as QHack. There's QHack in 2024 in February. Still, like the marketing is not out, but just keep an eye out for it, and keep an eye, like a lot of other quantum computing startups and companies do these things. And this is a good way to start honing your skills if you're interested in quantum computing. I must say that quantum computing, these skills are like very, very rare. So if you want to get into this, then you will probably get a job if you get to a high enough level. So yeah, and as you see, it's not terribly complicated once you get the hang of it, but yeah, it'll take a little bit. Yeah, if there are any questions, let me know.
Yeah. It's like you can go on a little bit more longer if you want, but like I'll ask you some questions and let's see what people where it will get us. And please join me with questions, but I'll start something simple. What you just showed us is something that the numbers are really nice, 0.5, 0.7. The quantum computers of today are not very accurate as far as I know it. So what we're showing is kind of an emulation, correct? It's not really.
Yes, this is an emulation. This is what we would expect the quantum computer to do if it was perfect.
Okay, and if I want to run it on actual quantum computer, what are my options? Can pennylane support it?
Yeah, pennylane can support that. Of course, you will need some key to the device or whatever, because some of them are paid and stuff like that. But yeah, what would change is basically the device here. You would change it into something like Qiskit Air or whatever you use for, which is a real quantum simulator, for example, or you could change it into, and we have a lot of plugins here. I can send the plugins page too. In which, if you change the device, how you define the device, you will actually run it in a real quantum computer. So
is it complicated, like to set up a quantum computer, or is it just like changing the name?
There will be a little. It's not as simple as changing the name, because you will also need a key that will be given to you by the provider, because using a quantum computer is usually not free. Okay, so you will have to pay. You have to create an account in AWS or IBM or whatever, and then you will have to play. Yeah, and then you can play around with it. But yeah, it is not easy. But the instructions of how to do it are in this plugins page.
Okay. And someone is asking, can you explain now the RAM works in a quantum computer? Is it not binary?
So this is actually a very active area of research, which is the quantum RAM. Basically, what we have to do is use a lot of auxiliary qubits that try to transport, that try to keep and remember some states. But again, this is difficult. This is difficult to do, because why is this so difficult? Again, because quantum states are not something that survive for too long. Okay, so we see the superpositions and they're nice, but as soon as we observe them, we destroy them. And there's a way in which the environment doesn't have to be humans who observe. If they interact too much with the environment around them, for them that counts as being observed, and it collapses. So yeah, but yeah, this is the quantum RAM is actually there. There are some proposals for how to use it, and it involves using more complicated circuits with a lot of auxiliary wires. But it's definitely not a finished research area. There's still a lot going on there.
So it will hold something like instead of like one qubit will hold one floating number or something like that.
Yeah. So one qubit would hold some floating number, but it would have to actually be like many that hold it, right? So you can encode it in many qubits, for example, or you can encode it in the numbers in the superposition as well. But yeah, there's just many proposals.
So you're saying it's something that's not currently defined. Proposals, you mean that people are just like now defining what RAM would look like?
Yeah, well, what quantum RAM would look like. Yeah, it's yeah. As you see, we're in the very, very, very beginnings of like this is some people are comparing this to trying to create a normal computer in 1879. So we're very, very, very beginners.
Can I add a little bit into that? So the physical computers that are made right now, the physical quantum computers, they're very small and they don't have very many gates. They don't have very many logic qubits.
Yeah.
So in a certain manner of speaking, they don't have RAM.
Yeah.
So it's to piece that apart a little bit. So you've got the quantum computer, and realistically, the quantum computer is attached to a traditional computer, because without the traditional step, I mean, you could have a quantum computer theoretically print to sort of like, you know, paper cards or something, but that nobody's realistically engineered that. So there is a traditional computer nearby, but you can think of that as sort of like a driver or an interface. The actual part that is the exciting part is the quantum the qubits themselves, and those are physically implemented in a complicated way that is often very, very cold. It doesn't have to be. There's a variety of physical implementations, but very often it's cryogenically refrigerated down to liquid nitrogen or lower, even liquid helium temperatures in certain cases. That physical substrate that's doing the computation doesn't, in a certain manner of speaking, the cold parts, they don't have RAM. So it's actually storing information and doing compute at the same time. So when you have it do a computational step, you have it do work without looking at it, and then when at a certain point you look at the state of the physical assembly and you read out its qubits, and whatever the value of those qubits are at that time, that is effectively the output of your computational step. And at that point, that is both the output of the logic and it is the memory itself. So the work being done in the future is adding in more qubits that are specifically added into the cold parts that are optimized specifically to store information, not necessarily compute on it. So that's sort of what the future of the quantum RAM will be.
Mm-hmm. Yeah, and I think it's very realistic to assume that all will be basically a combination of classical and quantum computers, right? We use quantum computers for whatever they're good at, and classical computers for whatever they're good at. Classical computers are very good at storing information. With qubits, it seems like it's a pain. So, yeah,
So I want to ask something interesting. So you're the very beginning of quantum computer. Let's say that the beginning of they haven't created the first transistor yet, and you were still running gates from tubes. This is what happened before the Silicon Revolution. But at some point, things started going very, very fast, and like Gordon Moore, he actually printed Moore's law that things will become faster by twice every period of time, like every year and a half. And this was correct for silicon-based computers, the one that we're using. Is this something that seems to be happening also in the quantum world? Because I remember reading about quantum computers 20 years ago, and you're telling me more or less about the same story. So
I'm telling you the same story for sure, but the number of qubits that we have reached is much, much higher. Like I remember when I graduated undergrad, I think we had like 5, and now suddenly people are talking about 256 and more. So the amount of computational power that we have with quantum computers right now is much, much larger than what we had a few years ago. We've also performed calculations in quantum computers much faster than classical computers can. Xanadu in particular has to do that, and people who do that claim what is called quantum advantage. The only thing is that the calculations that we can do are not useful for anything. So they're like esoteric mathematical problems that quantum computers can solve fast. So it with like again like a cherry picked problem, we can already do faster stuff. But the thing is that it's not only the hardware that has to improve, but also our knowledge of quantum algorithms and knowing what we can do with a quantum computer that also has to improve, and we have to figure stuff out there.
Can you describe one of those cherry-picked algorithms a little bit in more detail?
Sorry, which
One of the algorithms that is faster, that's like known, that's like it's easy to understand.
Okay, an algorithm that is easy to understand is Grover's algorithm, which is basically searching in a list. Okay, so imagine that you have a phone book, and I want to find a name of someone, but that phone book is not. No one uses phone books anymore. But let's say that it's all scrambled; that it's not in a particular order.
Oh, it's a random phone book. Okay, someone threw all the pages of a phone book to the floor, and now you have to reassemble it.
Yeah. So let me Google some things here, just because. Yeah. So that problem is called unstructured search. Okay, that's the name. And the thing is that if you were to solve this classically, the only way in which you could do this is by, well, I have to go through every single element in the list until I find the one that I want, right?
Uh-huh.
And on average, that would, if the list is of length n, then on average, you would be searching n-halves times, right?
Yeah.
You would go through n-halves elements until you find something. The thing is that with quantum computing, because of this superposition, you can kind of start looking, again, this is not the correct vocabulary, but you can start doing things at the same time because you have like the superposition of both qubits, that you can actually speed down the search, that instead of looking for it n times, you can do it square root of n times. You have to do it only square root of n. So it speeds up this unstructured search by a lot. That is, I think, a simple to explain problem that can be solved faster with quantum computing. It is not the best one. People are more excited about prime factorization. So multiplying two prime numbers and getting a large number is easy, but factorizing the number back is hard. And that's how our encryption algorithms generally work. That's also something that quantum computers could, in principle, do much faster. And that's why some people in the government and banks are feeling a little bit threatened. What they don't know is that we're probably decades away from actually achieving this. So yeah.
So quantum computers are code breakers, basically.
they're code breakers. They're searchers. They're not necessarily. We don't necessarily know what else they are good for. They're good at simulating quantum systems. That's something that they're really good at, and that's something that we have like a high hopes on it. Because molecules and atoms, in particular molecules, are quantum systems. And we would like to simulate behaviors of molecules. For example, for medicines, we would like to simulate how they interact with some molecules in the human body or something. So the way that chemists do it is just by trial and error and combining different things. But if we could simulate the molecules in a computer, then we wouldn't need to be spending like do so much trial and error and just simulate things. So that's also something that we would we would be able to do eventually.
Okay. This is interesting. So I'll ask a question later on. I want to explore more, but like someone posted that question: what makes quantum computers faster than conventional computing? It must be more than the fact that qubit stores more values than a bit. No?
Yeah, this is actually true. And there's something else that I didn't mention, which is entanglement. Basically, entanglement means that the qubits can be correlated with each other. Remember, they have probabilities, and they can be correlated with each other in very, very strong ways that ordinary bits cannot be. And this also allows for the speed up. Now, the full answer to your question, so this is what we know, that we know that there cannot be speed up without this phenomenon known as entanglement. That's something that someone published in 2002 or something. But the real answer is that we know as much, but we actually do not know what makes quantum computing faster than conventional computing. There's this intuition of like parallelizing computations, but it is very possible, like we don't even know, like we have still this P versus NP problem even in classical computing. So it's just, we don't really understand it very well, even without quantum. So what makes it faster? We don't know. We simply have found tasks by calculating by hand. We have found tasks in which quantum computers are faster. They are not faster for everything. And what makes them faster for those tasks? Some people say entanglement. The real answer is who knows.
Interesting. So you mentioned P versus NP. Perhaps explain it to some of our beginners. What does it mean?
Mm-hmm. So basically,
this is not related to quantum computing.
This is not. No, this is not related to quantum, but basically, I want to be precise, so I need to. Yeah, it just basically says that some problems, like P problems, are basically problems that can be solved in what is called in polynomial time, as in terms of the input of the algorithm, and those problems are said to be of class P. But there are others that cannot be solved in polynomial time in polynomial time, but if you have a solution to the problem, you can verify that it's a solution in polynomial time. So so the question is, are problems for which I can verify solutions in polynomial time also problems that I could solve in polynomial time? That's kind of the gist of it. That is unknown. That is an open mathematical problem. So I don't know. It could be that we don't understand a basic question such as this one. It could just be that that classical algorithms turn out to be as powerful as quantum algorithms. We just haven't figured out how. Peter's asking, what kind of tasks would quantum computers be slower at? That's an interesting question. I haven't thought about it. Well, anything that requires storing, for sure, memory, that would be one thing. I guess just think that they would be really bad at things that are very precise, and you cannot make many errors because there's always errors associated with quantum computing. So tasks that are very, very sensitive to errors, I would have to run the algorithm many, many times in order to get a proper statistics. That would also be something that quantum computers wouldn't be able to do, at least not anytime soon.
It is a very interesting question. My take on that would be, depends on really what you're asking. because there's a difference between the practical answer to the question versus the theoretical or formal answer to the question. So in practice, a lot of stuff would be slower with a quantum computer because quantum computers are physically implemented in a way where they're very big, very expensive, and almost always very cold. And they have a very significant sort of like initiation time in order to do the preparation, get it up and running, prepare your code. That's a relatively expensive process. So in practice, there's a ton of things that would be better that your computer would actually, a laptop would be better at beating. But in theory, at a formal level, the formal answer is nothing. The formal answer is there is nothing that a quantum computer would be slower at in compared to a traditional Turing computer. So, and that's sort of like a formality. It requires a whole bunch of academic assumptions in order to be capable of saying that, and that's related to. It's related to the fact that it comes from the fundamental nature of what computation is. So once you get a quantum computer that works, it can do all of the things that a traditional computer can do anyway. So you could reduce it to, you could specifically give a quantum computer like a task that specifically would never naturally be given to a quantum computer, sort of like as an academic showcase. And in that scenario, you could force it to go slowly, which would mean that you're proving that it's the equivalent of a traditional computer. But that'd be kind of weird, though. So why would you do that?
I would like to go back to what you explained about P and NP. NP is non-polynomial problems. Let's say something takes exponential time to solve or factorial time to solve. Is there other examples of quantum computers that solve something which is NP in good time?
There must be, but I'm not sure. None of the top of my
So
head.
so you couldn't answer the question 100%. Got it. But this will be interesting because if they can, then this breaks if you can solve one problem that's NP, how the reduction between those. And then this breaks the entire thing. But then again, it always assumes a Turing machine when you so which is basically a computer that is like available today, not a quantum one. So I was curious because you brought in P and NP. I was curious whether there is a solution of an NP hard problem that a quantum computer can do. But we'll have to leave it for another time.
No, that is prime factorization, right? That would be one, but I do not know of others.
So prime factorization is solved by a quantum computer, and it's an NP hard problem.
Well, it is NP, yeah.
Shor's algorithm runs in polylogarithmic time on a physically realized quantum computer. Yes.
Okay, slowly, without the high words. So you're telling me that there is an NP hard problem that is solvable in polynomial time on a quantum computer today?
I do not remember what is exactly the scaling of the time, the complexity of.
They're two separate things. I'm trying to piece apart whether or not it's NP hard. So I'm not. There's one question is whether or not NP hard problems can be solved. A separate problem is, are there algorithms that run in what I'm specifically saying is that Shor's algorithm runs in polylogarithmic time on a physically implemented quantum computer. And Shor's algorithm, among others, is that's effectively integer factorization, prime number factorization.
Okay, so let's leave that problem as possibly unsolved. We can discuss that later. There's a question from someone. I'm very much a newbie coming from a medical science background. So could a quantum computer in the future run simulations to give me a better picture of what's happening in some site in the body? I could get a broad imprecise picture that way, and then hone in on more precise results with classical methods? This is like a question from someone who...
Yes, in principle, that's the ambitious goal. The ambitious goal is that we can simulate chemical systems, complicated chemical systems using quantum computers. And yes, simulate, for example, the action of a drug in a body or in a particular person, even. Of course, it's a very ambitious goal. But yeah, definitely one of the applications that Xanadu is looking at, and many quantum computing companies are looking at, actually.
Daniel, I can tell you, I run disease models. One of the mechanisms that create disease model that's used in disease model simulation is what's called microsimulation or agent-based simulation, where you run many examples of the same thing and then run it again and again and again and again and again to see what the result is. It takes a lot of computing power because you have to run statistically the same thing. If I understand what Alvaro showed, then the quantum computers can do it much more efficiently, because instead of running it 10,000 times, they would run it only once. And then the entire computation will happen there. It may be far away from that, but in my understanding, this is one of the applications that will be very useful because instead of running it tens of thousands of times to get the distribution, you'll get it like that, because every qubit actually is kind of a distribution. But we're far away from that.
Yeah, it's more related to like simulating quantum system with classical computers is super difficult as well. So using a quantum system to simulate another quantum system is actually much more feasible.
Does it seem like... Oh, sorry.
Yeah, Danielle, yeah.
Go ahead.
Oh, well, I just got this idea in my head. You were saying it's somewhat imprecise. So I was thinking, okay, with the quantum computer could give you a broad picture, and then you could pair the two together in the meantime. No?
It's actually a little bit on the other way around, I would think. I would think the idea with a quantum computer is that it gives you a more precise picture than a classical computer could, because the way in which we model chemistry, for example, like chemical reactions or molecular structures, the way in which we model like the simulations that we do on current computers are approximations that ignore quantum effects. But sometimes these quantum effects can be very important to perform the calculation with a lot of precision. So, and it is these quantum effects that we cannot simulate really easily. So a quantum computer could account for these quantum effects and simulate with much more precision.
Yeah, I think I was trying to follow along and reversed it in my head. Thanks for clarifying that.
No worries.
Yeah. So it might be the inverse then, that we would use classical methods and then quantum methods.
Yeah, quantum methods to refine.
Okay, okay, thank you.
Danielle, we kind of actually still don't know. This is what Alvaro is telling us. We're still exploring how this new tool can be used.
Yeah,
yes.
But ambitiously, this is the goal. Yes.
Thank you. Thank you.
Peter is asking something, but a lot of text. Let's see. Are all quantum computers in the world in the facility similar to the Institute of Quantum Computing in Waterloo, where the building is mechanically isolated from the surroundings? Why is this necessary, or is it necessary?
Yeah, all quantum computers in the world, yes. They are in a facility which has to isolate external noise, vibrations, temperature in general really, really well. That is because there's something in quantum mechanics that is called decoherence. Decoherence basically destroys or modifies your quantum state. So your qubit, like those coefficients that you have, which have to be very precisely a number, if if the qubit is exposed to the elements, to the environment, to even like a little bit of light, to some temperature in the environment, that can change it, and that can ruin the precision of your calculation. So in principle, yes, we need, at least as far as we know, to isolate the quantum computers in a way. Now, for example, Xanadu has their like the quantum computer that we built. It can function at room temperature, except for the measurements. The measurements that you do at the end, that cannot work at room temperature. But still, we don't have it in like such a fancy facility that it's everything frozen and mechanically thoroughly isolated. There's only a part that is isolated. So it depends on the quantum technology that you are using, how much isolation you will need. There's also hopes, for example, some people are using superconductors to do quantum computing as well. That can, some people are looking into superconductors that work closely to at room temperature. That could be a thing. I don't know how possible that is, but again, yes, I think in principle, and as far as we know, we need to isolate. Is it necessary? Might not be in the future. It is now.
Yeah. Alvaro, you have more questions. You're engaging our audience, so if it's okay with you, can you answer a few more before we close? So people are talking about, they're just like, you see it in the chat, they're like excited and writing it in like not even question form, but people are interested about machine learning and quantums. Someone who wrote it as QML.
I'm not an expert in the topic, but definitely it is something that people are looking into, basically ways to use quantum circuits to encode some classical data and then try to fit some models to it. Now, the thing with what quantum circuits or quantum algorithms is that the models that they can fit are different from the models that we can fit, for example, using a classical neural network. So we are looking into, we are at this stage and we were looking, okay, what can we do with it? Does this solve interesting problems? Because basically classical computers can deal with a lot of data and can fit like almost anything to it. So the question is there any benefit in using these quantum circuits to actually fit data for models that classical computer don't find too easy to implement? So that is the question, and we don't know. It's a research area, but it's something that could happen in the future.
This is the new frontier, apparently. And someone like Peter said, so we won't see quantum laptops in the near future. Well, Peter, probably not. But to remind you, the first computers that were ever constructed were made out of machinery, like mechanical machinery, or all sorts of other things like tubes, like vacuum tubes. And they would take whole rooms just to compute. And this was not that long ago. It was less than 100 years ago. So what we are staging quantum computing is very similar to what there was before. So this is why we may not see laptop computers in the quantum computers in the near future, but you have to see what will happen in the farther future after this. And someone is talking with me. I'm trying to figure out who it is. Okay, yeah. Yeah, okay. Hopefully we solve that problem. So we may not see it now, but we may see it in the future.
Sorry.
Okay. So this was my talk to Peter. Anyone has any more topics that they want to raise to Alvaro?
I'm sure many of us are using, Chat GPT or Bing or Bard for doing Python programming. I'm just wondering, how useful are those AI bots for something that's this advanced? Are you able to use it in your day-to-day job?
ChatGPT, it's something that we're actually looking into.
Uh-huh.
So far, it hasn't been too useful. For example, we did QHack, where we have like some coding challenges for like basically a penny lane competition, if you want,
Yeah.
for solving problems. And ChatGPT came out like the month before, and we were just like looking into if ChatGPT was able to solve the challenges for us and for like potential participants.
Uh-huh.
But it wasn't very good at it, at least back then.
Right.
So for the moment, no. I wouldn't say ChatGPT can actually solve these problems, like quantum computing problems, very well.
Right.
But who knows in the future? I mean,
Right.
yeah.
Interesting.
Any more questions to Alvaro, or questions going once? Question going twice? Question going 3 times? Okay, it seems that you have answered most of our questions. I assume not. We probably have many, but we can probably talk about it after we finish this recording. But before that, I want anyone to clap, make some noise, some reactions. I want to thank Alvaro for joining us, telling us something very interesting in a very nice way. Thank you so much. It's been a really, really good lesson on quantum computing. I really, really appreciated that you gave it to us.
Thank you so much for having me.
Yeah. So stick around. We're not going away. I'm just finishing the recording.